Okay, so this is where we were on Friday. We start with the nonlinear SVM formulation, and then we talk about feature embedding. And then the sweet thing about SVM is we don't even need to visit that feature space. We can use a kernel function. And then we talk about how to pick the kernel function K. The choice 2 would be sort of the general framework. You can pick any bivariate function K as long as it satisfies the so-called Mercer condition. And basically, the K should look like a kind of a covariance matrix, so you can do singular value decomposition in the sense that you can think about your K and can be expanded as sum of J from 1 to capital M, an eigenvalue times a basis function gjx and gjz. So this sort of the M could be infinity, and usually the eigenvalues are arranged from large to small. And once we know the K function look like this, remember the K function represents the linear product in the feature space. Then you quickly can extract what is the corresponding feature mapping. So the feature mapping would be phi x is equal to lambda 1 and g1x, lambda 2 as the second dimension, and all the way to lambda m gmx. So here the function g's are the basis functions going to take the whole p-dimensional vector as the input. The mapping may not be unique, but that's the same as we discussed many times. For linear subspaces, they may not be unique, but as long as the underlying inner product is the same, then that's the same space. And then to illustrate this Mercer condition, and I showed you for Gaussian kernel, suppose we're in a one-dimensional space, then we can rewrite the Gaussian kernel as those infinite sums. So what we did is we extend the exponential component. So we have minus sigma x squared, minus sigma z squared, and then the remaining term in the exponential component is 2 sigma x times z. And then for that last term, I just expand that expansion, because the exponential function can be written as an infinite sum of those polynomials, start with k equal to 0. So we can do that. And then we can start merging things together. We're going to find out the functions in red will be the function applied on x, and the function in blue will be the function applied on z, and they are basically the same set of functions. Of course, right now, those blue and red functions are not basis functions because they're not orthogonal to each other yet. But that's not too difficult. You can just start sequentially orthogonizing them. So that's just the next stage. So basically, this expansion for Gaussian kernel indicates that the Gaussian kernel actually corresponds to an infinite dimensional feature space. And this kernel, it corresponds to the inner product in that space. Okay? And so this is for the Mercer condition. And then at the end, I said, actually, it's okay to use any other kernel function k as long as it is symmetric and as long as it represents the similarity between two samples. And the reason is, then we went through some of the discussion. The key idea is that we realized for SVM, although you can think about it, we are building a function either linear or nonlinear in the X space, but there is an equivalent way to think about what is that function. You can think about that function as a linear combination of k functions, and those linear weights will be lambda I and yi. So in short, you can find out the kernel function can be written as, it's okay to think about the function learned from your SVM is a linear combination of those functions. What are the functions? And we have our bivariate kernel function k. You fix one argument at one of the data points. So we have n such functions now. And you just do a linear combination of them. Then we want to learn what are the alphas and what are the what is the intercept alpha 0. And in particular, you're going to find out the evaluation of this function f on the n data points, and it's basically a matrix k n by n times the slope alpha and plus alpha 0. So once you can think about your model like this, And then you are free to use whatever K functions, because now the K is basically kind of a new design matrix in your setup. So you can get your K matrix and K, your matrix K, your design matrix K n by n, and then you need to estimate the alpha and alpha 0. Then you can formulate your problem as loss plus penalty, and you can use whatever loss function you like. And for the penalty here, we do the rich type penalty on alpha due to the formulation from SVM. But now you're free to use whatever alpha and penalty you like. You can do L1 penalty too. And further, one of the big computation burden for SVM is that the complexities in terms of sample size, not the dimension p, because you have n parameters you need to estimate. So for a simple problem like a two-dimensional feature, but if you have 10,000 observations, the computation is still very, very heavy. Well, but once you get your K matrix, you can do PCA. You can reduce the dimension instead of estimate, maybe top 10 eigenvectors times a W, which is only 10-dimensional. So you are free to use a lot of other approaches at this moment now. The resulting model may not be categorized as SVM, but who cares? As long as it will solve the problem you have at hand. Okay, so then I spent some time to describe if X indeed satisfies the Mercer condition, and we can see something more about the underlying framework, and it's really with RKHS. But I put this as optional, and I did prepare some video for this. You will be able to see that maybe later this week on media space. So I'm going to skip this at this moment, but feel free to talk to me if you want to know some details. I prepare a summary video for SVM, but let me just quickly go through that right now. So for SVM, think about the soft margin formulation. Ignore the hard margin, because you're going to find out hard margin basically is a special case of the soft margin. So what is a soft margin formulation? Start with linear SVM. Our goal is to place a wide yellow avenue. Well, you cannot see that yellow avenue on this screen, but you can see that on this slide. We want to place an avenue to separate the two groups of data points. How we find out the optimal avenue? We formulate our objective function as a sum of two terms. The first term is reciprocally related with the weights of the avenue. So when we try to minimize the objective function, we basically want to maximize the margin. And the second term is a tuning parameter gamma. Gamma is always non-negative, times the sum of loss or error on the n data points. So what's the error? When we place an avenue to separate the two groups of data points, ideally we want the data points to be on the correct side of the dashed lines. So nothing between. And that means for every data point, we want yi times this linear function to be bigger or equal to 1. But sometimes this inequality may not hold at some data points. So for those data points, we're going to lower the right-hand side by subtracting some positive number psi I. So that psi I will be the error at the ith data point. So our final objective function is a combine of the two terms. And we want avenue to be wide, and meanwhile want to minimize the error. And there is an equivalent representation of this primal problem in terms of hinge loss plus a rich penalty on the slope beta. There's a one-to-one correspondence. When gamma here, if it is infinity, that means we basically cannot tolerate any error if possible. So that back to the hard margin formulation. But in general, our gamma will be some number just bigger than 0. So the gamma and that nu on the right hand side, and there's a one-to-one correspondence, and they're reciprocally related. So when gamma is large, the price you pay for error, you pay more price, actually means less regulation, means more complex model, means danger to overfit. Okay, so they're reciprocally related. So this is a primal problem for linear SVM. That's the objective function. Once we solve, we wanted to get the slope beta and the intercept beta 0. But in practice, we actually solve the dual problem. The dual problem is formulated as a max over n parameters, lambda 1 through lambda n. They are the Lagrange multipliers, one for each data point. And so we can solve the dual problem, and through the KKT conditions, once you solve the lambdas, you can actually retrieve the beta and the beta 0. But you don't have to. You can just stick to your lambdas all the time, because even for prediction, when we do prediction, ideally we wanted to plug into, retrieve that beta and the beta 0, basically that solid blue line. That's our decision boundary, right? On one side is +1, another side is -1. But because of the KKT condition, that solid blue line can be represented by some function only in terms of lambdas. So you can just get your lambdas, and when you do prediction, you stick to your lambda representation. So there are two advantages of working with this lambda representation. Advantage 1, a lot of this lambda is going to be 0 because of the KKT conditions. For example, for this particular case, only 4 data points going to have non-zero lambdas. The other data points either on the on the dashed blue lines or on the wrong side of the dashed blue lines, and they are called support vectors. So in terms of the lambda representation, the SVM is actually sparse. Another advantage with the lambda representation is when we want to learn a nonlinear decision boundary, what we do is we're going to embed our data, our original p-dimensional feature, into a higher dimensional feature space. Then any linear function in the higher dimensional space correspond to a nonlinear function in the lower dimensional space. And with the lambda representation, you're going to find out we don't have to construct that mapping. All we need to know is how to compute the inner product in that feature space. So you can replace all those dot product by those kernel function k, and everything the same as original linear SVM. So popular kernel functions will be like Gaussian kernel or polynomial kernels. And what I said at the very beginning of this lecture is just to take a different view of SVM. Just realize for nonlinear SVM, what we have learned is basically a combination of those kernel functions. For example, let's take a look at what the f function look like. Suppose x is one-dimensional and you observe 3 data points. Okay. For all the kernel functions, the kernel function going to give you a large value if the 2 arguments are close. Right? Makes sense. So hypothetically, suppose you use those step-wise kernels, meaning your kernel function at x1 would look like this: 0, and then just there is a bump. And the kernel function with 1 argument fixed at x2 will be 0, and there's a bump around x2. Again, for x3 will be just 0, and then there's a bump at x3. So those 3 functions correspond to that 3k functions with 1 argument fixed at x1, x2, and x3, right? So we are learning a linear combination of them, which is basically very much similar to 1 nearest neighbors, right? Agree? And of course, if you use Gaussian kernel, then things will be much more smooth. So this is why SVM is essentially just a kernel model in some sense. And if you wanted to do your kernel model this way, it is possible you probably won't be able to use SVM packages, because I don't think they have, what I mean is if you want to use your own kernel function k, you probably have to extract the k matrix to, set them into other packages, because I don't think SVM can allow you to design your own kernel. But that's fine. You can just take your k and you can run a linear regression, logistic regression model. So any questions? Okay. So actually, I'm not going to talk about new stuff this lecture. I want to answer some questions popped up on the discussion forum. One of the questions is about linear classifiers. So far we have learned a bunch of linear classifiers, LDA is one of them. And we talk about logistic regression, and we talk about linear SVM, right? So that's three linear classifiers. And I didn't talk about nonlinear classifier or quadratic, but if we could understand the linear classifiers better, we would be able to understand other classifiers. Now let's just talk about the difference or similarity of those three classifiers. For LDA, we estimate binary LDA. We estimate mu1, mu2, sigma, p by p, and then we basically know. Well, we also have to estimate maybe the frequency of the marginal frequency of y. But once we know those parameters, we know the joint distribution of x and y. Agree? And then we can plug into the formula. For binary classification, we basically wanted to look at the ratio of these two probabilities. P of y given x, what is the ratio of p equal to 1 versus p equal to 0? Oh, sorry, it's not bigger than 0, should be bigger than 1. Or in the sense, if the log of this is bigger than 0, that's basically our decision boundary, right? So when we try to classify whether a point is from class 1 or 0, we basically evaluate log of this likelihood ratio. If it's bigger than 0, it's in class 1, otherwise it's in class 0, right? And you can find out if you can check the notes for LDA, eventually this decision boundary, which is log of the likelihood ratio, is that bigger than 0 or not, and correspond to a linear function. X transpose sigma inverse times the difference of the two groups, and plus some kind of an intercept. And agree? So sigma is the shared covariance matrix, mu1, mu2. So the sigma, mu1, mu2, we can estimate them from the data. So the decision boundary is a linear function. And if I pile those things together, which basically is our slope beta, okay? Or maybe I call that alpha, just to match with the intercept is noted by alpha 0. So this is p-dimensional, okay? But meanwhile, let's look at how we estimate logistic regression. So in logistic regression, we just directly model log of this likelihood ratio. And we model the log of this. Again, I forgot the log. So we want to model log of this as a linear function. X transpose beta plus beta 0, right? Then we use MLE to estimate beta and estimate beta 0. Agree? So if data are generated from a mixture of normal, like what the LDA specified, so if data are generated from LDA, meaning we know the whole data generating process, and then if I get enough data, the linear function from my LDA and the linear function from my logistic regression should be the same. Agree? Because they are in LDA, you basically wanted to learn log of this likelihood ratio. It's a linear function. And in logistic regression, you directly model this as a linear function. But when the truth is a linear function, of course they are the same. Okay? So if data are generated from LDA assumption, then they should be the same. And when we have enough data, so asymptotically. Now, of course, if you are provided with a finite samples, the two estimates always differ a little bit because of the objective functions are slightly different. Okay? But what's the difference between logistic and LDA is in logistic, I never talk about, how can we generate data from logistic? In logistic, we only put assumption on the distribution of y given x. We never specify any assumption on x. So your x could generate in a different way. So in general, I would say in terms of the model assumption, LDA specify, if I think about the model assumption for logistic regression, then LDA is only a subset of those, because the assumption for LDA already implied some assumption on the marginal distribution of x, but in LDA formulation, we never specified the assumption on x. X could be anything, generated in many different ways. Okay, clear now? So difference between LDA and logistic regression. In short, if data are generated from LDA, because LDA put a stronger assumption that kind of assume the whole data generating process. So if data are generated from LDA, then asymptotically the two methods should give me the same linear decision boundary. Okay. Now, what about linear SVM? So when we talk about linear SVM, there's no model. We directly learn the so-called max margin separating. It's a linear decision boundary, right? So the question is, how can we link what we learned in linear SVM with the underlying distribution of X and Y? So when you just look at the linear SVM, it seems like we never made any assumption. How can we find out, how can we draw the connection between the data generating process and the linear function we learn? Well, whenever somebody or some algorithm use some objective function to find their classifier, you can always draw some connection with the data generating process. Why is that? So in SVM, linear SVM, we basically try to minimize the hinge loss. Yes, there's some kind of penalty there, but asymptotically, if you have an enormous amount of data, you will never use any penalty. So the penalty will drop, okay? So in linear SVM, if we have enormous amount of data, almost we know the data generating process, we try to pick a function f to minimize this hinge loss, okay? So let's find out, suppose we know the data generating process, we know P, X and Y. In the ideal scenario, we know the data generating process, join the distribution of X and Y. Then what is this optimal function f that minimizes the hinge loss? You're going to find out that minimizer depends on the distribution. So it turns out, I'm going to show you the optimal function f that minimizes the hinge loss is like this. So your fx, let me do star. Now in SVM, we represent our y not as 0 or 1. We actually represent our y as 1 or minus 1. Right? So our prediction would be your prediction should be 1 if your eta x is a symbol I used before, is a conditional probability of y equal to 1 given x. Okay, so if eta x is bigger than half, otherwise it's minus 1. Okay, so that's the optimal decision boundary. So we know, so you can see actually for linear SVM, if we give the machine enormous amount of data, the optimal decision boundary actually the same as the Bayes rule. We still make our decision based on the conditional probability of y given x. Okay, so let's see how we can prove this. So linear SVM, we're now going to just take the hinge loss and we ask ourselves, suppose we know the data generating process, then we can evaluate the expected hinge loss. Again, what is the hinge loss? Y is going to be 1 or minus 1. Fx is going to be any function that's going to take x as input and output some real number, okay? And our loss is evaluated as 1 minus y times fx. If that difference is bigger than 1, bigger than 0, take that number. If that difference is less than 0, then just treat it as a 0. So our hinge loss is like this. Oh, should I take the positive side or negative side? The hinge loss. Oh, yeah, right. Because when y times fx is negative, sorry, this is not 1. This should be 1. Here is 0. Right, so this is a hinge loss, yeah. So let's find out, suppose we can do all the expectation calculation. What is the function f that can minimize this risk? And if you could remember what we did before in the very first lecture for classification, how we handle this and try to find the optimal f, the expectation is actual expectation over both x and y, right? So we break the expectation, rewrite the expectation iteratively as the outside expectations over x and inside expectations over y given x equal to a little x, right? and then we do our hinge loss. Here. So in my representation, so this is what we used before. When we try to find out what is the optimal decision rule that minimizes 0, 1 loss, we actually focus on inside, right? For example, for every little x, every value of x, every feature vector x, if we could find out the value, which is fx, can minimize this inside expectation, meaning we're doing optimal at every location of x, then the risk for the whole function f must be optimal. Okay, so this is what we're, this is the, meaning this will be the expectation I try to minimize. How we minimize this? We are conditioning on a particular x. The only thing random is y, and y is only binary, 1 or minus 1. So the probability of y equal to 1, I denote it by eta. You can ignore this as a function of x, meaning x is fixed now. So the probability is eta, and the probability of y equal to minus 1 going to be 1 minus eta, right? Then let's look at the fixed location x. What is the optimal value a we need to assign to fx to minimize this expectation? First, let's evaluate this expectation. Well, y is binary, take only 2 values, so the expectation basically the sum of 2 probabilities, right? So when y is equal to 1, the probability is eta x, and then y times a is just a. When y is equal to minus 1, the probability is 1 minus eta x, and then y times a is going to be minus a, so that minus sign becomes plus, okay? So we ask ourselves, now in this expression, eta is given. The only thing we don't know is a. How to pick an a value which can minimize this? First, we wanted to conclude that the a must be between minus 1 and 1. Okay, because a could be any number, right? So let's do minus 1 and 1. Okay, suppose a is bigger than 1. If a is bigger than 1, of course, this part is just going to be 0, right? You're just going to ignore. So if a is 1, a is bigger than 1, then you're going to find out what's relevant is just going to be this term, and this term is always positive. And you want to minimize things, right? So you have to force your a to be 1. You can do the same argument to find out, well, your a shouldn't be less than minus 1, 2, okay? So once your a is between minus 1 and 1, and that those 2 terms, you can drop that subscript plus because it's always positive, okay? So you can rewrite your stuff like this. And then you can start merging things. 1 times eta x plus 1 times 1 minus eta x is going to give me 1, okay? And then let me start merge stuff associated with a. I get a minus a. Oh, I think I made a mistake here. This part should be, oops, 2 eta x minus 1. Is that right? Because I have a minus sign here. Agree? Right. Or if I want to keep the original expression, then I have to make this to be plus. Because a times eta x is always negative. I have 2 copies of that, okay? So now this is our objective function now, and a is between minus 1 and 1. And then you're just going to do the following argument, discussion. Suppose your eta x is less than a half. Okay, meaning at the location x, the chance of y equal to 1 is less than a half. If eta x is less than a half, 1 minus 2 times eta x is going to be positive or negative? Going to be positive. And you want to minimize this. So you want to make your a small. So you're going to find your a should be equal to minus 1, right? So if your eta x is bigger than half, then your 1 minus 2 eta x is going to be negative. Again, you want to minimize this. So you want to make your A to be positive, very large. So you get A is 1. So this is the optimal decision boundary learned by SVM if you give SVM a lot of data. You basically, it's just the sign of eta x minus a half. So the decision rule is almost the same as the base rule. You just look at every location x, if your eta x, the chance of y equal to 1 is bigger than the chance of y equal to minus 1, classify or predict y to be 1, otherwise minus 1. So once we have that discussion, then we realize, well, again, because only LDA gives this, well, actually even here. So if data are generated from logistic assumption, meaning your y could be anything, but x could generate in any distribution, but your y, the conditional distribution of y given x, and that logic should follow a linear model. And then you know your linear SVM and logistic regression should give you the same answer. Agree? Because this is optimal. This basically is the logic of eta x divided by 1 minus eta x. Okay? So in short, a lot of this linear classifiers we have learned so far, although for finite sample, the solution might not be the same because the objective functions are slightly different. But in asymptotically, if data are generated from those assumptions, then they should usually give you the same answer. Okay, questions? Okay. Okay. One difference between the three methods is is a feature selection issue. And for logistic regression, we can use L1 penalty to directly select the feature, and we can do cross validation. And for LDA and also linear SVM, and there's no built-in feature selection and tool in the algorithm, meaning in the optimization. So you have to do some pre-processing to drop some noise features. But for logistic regression, you just add a penalty, so it's easier for feature selection. Okay. And this is a commonly asked question for 542, and I also know this is a commonly asked questions during interview, is how to deal with imbalanced data, and sometimes you may call that unbalanced data. And when we say imbalanced data means you have your data set is a binary classification problem. Now I'm switched back to y is 1 or 0. So you have many data from one class. Without loss of generality, assume we have many data from class 0, but only a few is from class 1. And the issue with this kind of data is that if we use misclassification rate as the metric, you're going to find out it's very difficult to beat this naive procedure. We basically predict everything from class 0. Okay, so I post something on a discussion forum. First, I want to point out there's nothing wrong about predicting everything just from class 0. Agree with me? And I mentioned about that serial kind of a marketing example. Anybody read the post? Or if you haven't read the post, please raise your hand. You did or you didn't? Oh, okay. So maybe I'll put out that. And I'll need to put out that discussion. Sorry. Where is it? Imbalanced data. So the reason I create this post is for our lending club data. The data is slightly imbalanced, and definitely we have more from one class and less from the default class. And when I assigned this project before, students like to ask me, and they said, well, since this is an imbalanced case, and shouldn't we use AUC as a metric instead of log loss? Because I asked to use a log loss. But I feel like this is a wrong question to ask, in the sense the choice of the evaluation metric should be determined by the problem you have instead of the data. Of course, here, because it's a course project, we really don't have the question because you are just signed with this project. But I give two scenarios. I'm afraid my online students wouldn't understand what's Meyer and what's Carl. So you can imagine in case one, the marketing team wanted to decide, and they collect some data and they want to decide which of the two products they like, A or B. Then they can try to send the appropriate coupons to those customers. But hypothetically, you find out most of the people actually like A, majority of them like A. And then when you learn and there may be a few like a B, but they're so mixed with that group of A, it's hard for you to find out a classification rule you can sort of single out this, class B customers. And so you will probably just end up using that trivial classification rule and classify everybody's from class A. But there's nothing wrong about it. If most of people like A, just send out coupons for A. In terms like the final benefit of this coupon, you still get, it can be well captured by 0-1 loss, so it's fine. But of course, usually the issue with the imbalanced data, I think I can switch back to this slide now because this is so busy, this page. But usually is the underlying loss function actually could be different for the two groups. Imagine, class 1 will be patients, class 0 will be non-patients. And so there are two types of errors. If you classify a patient to be non-patient or classify a non-patient to be a patient, the consequences may not be the same. So this, but if that's the case, just change your loss function, because the sort of a cutoff at 0.5 after we get the probability is basically based on the symmetric loss function. By symmetric, I mean our loss function, the misclassification rate, is always this, right? So no matter you, but there are two types of errors. One is, your y is 1, but your fx is 0, and plus y is 0, fx is 1. For any sample, you will only appear in one of these indicators. Well, not this one anymore. But if the arrows are different for the two group of arrows, you may want to assign them. Maybe this is the price you pay for. There are different price 1 and price B. And when you try to minimize this weighted sum, and naturally you're going to find out the cutoff is no longer a half. It will depend on the ratio of A and B. So that will definitely change this problem. But sometimes you don't really know the underlying loss function, but you just wanted to. In some applications, what's really relevant is the ranking. For example, a lot of this classification model are used for recommendation. Let me just use one example. You get a bunch of products or articles you wanted to recommend to customers. You can learn whether this customer going to like those articles or not. So you basically want to predict whether you're going to like or not like it. So you can get probability. But it doesn't matter what the value of the probability. All you care is which two articles that probably the highest. Then you're going to recommend those two. Those two could be in the movies, right? So all you care is the ranking. All you care is what is the probability, the ratio of the probability of y equal to 1 given x equal to x1 divided by y equal to 1 given x equal to x2. So in that case, then the AUC will be a good criteria, because AUC is basically measuring if you pick 2 points from the just randomly pick 2 samples, and what's the order of the probability actually the same. So that will give you, and so instead of using those like classification error or log loss, you may use AUC and depend on the underlying task. A very popular approach, which is also based on what I heard from students, are the answers people who interview want you to answer, is a so-called sampling-based approach for imbalanced data, and either downsampling or upsampling, meaning they want you to either adding weights or do some downsampling or upsampling to come with some new training data. In that data, the 2 groups are more balanced. I don't see any theoretical justification for this, but I believe it is true sometimes for some real problems may work. It's okay to use this approach, but don't forget to calibrate your model. Why you need to calibrate? If you fit a lending club data where in the lending club data, half of the loan going to default. Well, let me use a credit fraud data. You hired by Capital One, you want to learn how to predict whether somebody going to have fraud for the credit card or not. You do some sampling and you're training your classification model based on a data where half are fraud, half are not. And then you take that classifier you want to apply on the general population. Apparently going to make a lot of false positives, because in the general population, very few actually going to commit fraud. So you have to calibrate your model. What I mean by calibrate, it's easy. We have to use we used actually one of them already, which is the Platt scaling. So what I mean is you have your data, training data, you go through some sampling stage or whatever, and you come with some prediction that's called a QI. QI is a number between 0 and 1 because you're doing probability. And you have your original data, YI, which is binary, right? Then how you do Platt scaling? Fit a logistic regression model with one numerical feature, which is QI. Very simple, right? That's how you do scaling. So what is the meaning of the scaling? Well, you have your QI, which is between 0 and 1. But you feel like the QI may not be right. You want to sort of do some stretching. For example, maybe during the range of 0.7 to 0.8, you have to lift the QI a little bit, or maybe drop the QI a little bit. So you basically want to find out a mapping between 0 and 1 to another 0 and 1. Sorry, it's not a rectangle. So you want to learn a curve, and you want that curve to be monotonely increasing. Agree? Right? Because you cannot, if previously, for one sample, the Q is bigger than in the new mapping, that P, let me call this P now, you want to map to the probability, you want to be monotone increasing. And so the Platt scaling, which you use the logistic regression, is one way to find out mapping, but you can go with non-parametric. So one approach is called the isotonic regression. So you do a non-parametric regression, use those step functions, but you want to fit your regression in a way you make sure the curve is actually increasing. So you're going to fit a function f, take q, output a probability p, and it's an increasing function. And you want to learn this f in a non-parametric way. And there are some packages available, so you can just call them. Okay. So there are 2 of the approach for calibrate. And the key issue is once you manipulate the sampling of your training data, then the training data may not be a good representation of the future population. So you have to calibrate, okay? Now, why I feel like the sampling is not really, I don't see any theoretical justification, in the sense that sometimes we just use logistic regression and we can really unbalanced, and the results still meaningful. So here's one paper from Professor Owen and from Stanford. I attached the paper link and his talk on Piazza. So in his paper, he considers the following scenario. We have our data from 2 classes. Y is equal to 1, y equal to 1, and we have n sub 1 observations, and y equal to 0, and we have the capital N observations. And we're going to consider the extremely imbalanced scenario means n, uppercase N, is much, much bigger than n1, lowercase n1. In the extreme case, big N is infinity. So we already know the data generating process for this class 0 group. And then we can still fit a linear regression model. You're going to find out for the logistic coefficients, their intercept and the slope. The intercept will go to minus infinity because the disproportion of the two groups. But the slopes are still very meaningful. I don't think I have time to go through this, but I want to show you an example. Okay, so this is the hard data we analyzed before using logistic regression. So we have roughly 300 from class 0, and roughly about a half, like 160, half of the size is from class 1. So slightly imbalanced, okay? So we run a logistic regression. And then what I'm going to do is I'm actually going to merge class 1 as one data point, okay? So I first find out what are the data samples that are from class 1. Then I will just basically generate one row of the data. All the observations are the average of the corresponding features, okay? So I have my new data. What my new data look like? 302 are from class 0 and 1 observations from class 1. Okay. Then you run a logistic regression with this new data. Here I compare the coefficients from the two logistic regression model. The first column is from the original logistic fitting, and the second column is from this weird data where we only have 1 observation from class 1. Okay. So you're going to find out, apparently you're going to expect the intercept to change. So the intercept for the second scenario will move further to the negative side because of the imbalance of the two groups. But if you look at the coefficients for the other, the change is actually, I would say, relatively small. If I do have enough, enormous amount of data, I just set my class 1 as 1 point, you're going to find out those other slopes are still very similar. So that back to the question, in a lot of cases, if all you care, I dropped that part. If all you care is the ratio of, for 2 observations, which one is more likely from class 1? If you care about this, you run logistic regression, you're going to find that intercept disappeared. We don't care about the intercept. All we care are the slope beta. And then you could actually, for that extremely imbalanced data, you can still get very meaningful outcome for this ranking. And I attached some of the reference for this paper. It's very interesting. And I wanted to explain. Let me just use 2 minutes. Let me explain what's the final theorem. Okay. So the final theorem is like this. Let's consider extreme imbalanced case, meaning for class 0, we almost know the data generating process, okay? For class 1, we only observe the average, 1 data point, okay? And then we try to ask ourselves, if we do a logistic regression, what's the meaning of beta? And turns out the meaning of beta is the following. Imagine you have your data are one-dimensional. This is the data from your class F0. I draw it as a normal. So it's from F0. But for your class 1, you don't know the data generating process, but you know the mean for your class 1 is here, X bar. And then what this one's doing is you said, well, I have data only from F0. I have a bunch of observations. How can I start weighting my data? Because I'm basically trying to, put the data from the original F0, I'm going to generate a new distribution now by start weighting those, adding weights to the data. The exponential tilting is what they said. How we weight our data. For example, previously, if data here, you get lower probability under F0, but now we're going to boost those weight. How can I do this to make sure when I generate my data from the F0, but once I do the rate weighting, they almost look like the data from the F1 because the mean is the same. So that kind of, well, I can talk more about this next time. So this is a kind of very interesting. You're going to find out for logistic regression, that beta is exactly the slope. So even in this extreme imbalanced case, you can fit a logistic regression model. You probably have to drop the intercept, but the slope parameter is still very meaningful. Okay.